Many people think Neptune is the coldest planet in our solar system. It's the farthest planet from the Sun. It looks icy blue. It orbits in the dark outer edge of space. It must be the coldest. But that assumption is wrong. The coldest planet in our solar system is not Neptune. It's Uranus. And what makes this surprising is that Uranus is actually closer to the Sun than Neptune. If distance alone determined temperature, Neptune should easily take the title. It receives less sunlight. It sits farther out in the darkness. By simple logic, it should be colder. Yet when scientists measured the lowest atmospheric temperatures ever recorded among the planets, it was Uranus that reached the more extreme lows. In fact, Uranus has dropped to around -371 degrees Fahrenheit, making it the coldest planetary atmosphere in the solar system. So how can a planet that receives more sunlight end up colder than one that's farther away? To answer that, we have to look beyond distance and into the strange internal physics of these two distant worlds. To understand why Uranus holds the record, we first need to look at what these temperatures actually mean. Neptune's upper atmosphere can drop to around -330 degrees Fahrenheit. That's unimaginably cold by Earth standards. Far colder than Antarctica, far colder than anything naturally occurring on our planet. But Uranus has been measured at even lower extremes, reaching roughly -371 degrees Fahrenheit in its upper atmosphere. That difference might not sound dramatic at first, but in planetary science, it's significant, especially considering that Uranus is closer to the Sun and receives slightly more solar energy than Neptune does. If sunlight were the only factor controlling temperature, Neptune should clearly be colder. But planetary temperatures aren't determined by distance alone. A planet's internal heat plays a major role in how cold its atmosphere becomes. When giant planets form, they trap enormous amounts of heat from gravitational compression and leftover energy from their formation. Over billions of years, that internal heat slowly escapes into space, influencing atmospheric temperatures from below. And this is where things start to get strange. Neptune still radiates significantly more heat than it receives from the Sun. Uranus, on the other hand, barely emits any excess heat at all. And that difference may explain everything. Uranus is one of the most unusual planets in the solar system. Unlike every other major planet, it rotates on its side, tilted at an angle of about 98 degrees. Instead of spinning upright like Earth or even Jupiter, Uranus essentially rolls around the Sun like a barrel. This extreme tilt creates some of the most dramatic seasons in the solar system. For decades at a time, one pole faces the Sun continuously, while the other remains in darkness. Then, as Uranus continues its slow 84-year orbit around the Sun, the situation reverses. Entire hemispheres experience prolonged summers and winters, unlike anything seen on Earth. At first glance, this strange orientation might seem like the obvious reason for its low temperatures. Long periods of darkness could allow parts of the atmosphere to cool dramatically. But Neptune, despite lacking this extreme tilt, is still not colder overall. The tilt alone does not explain why Uranus reaches lower minimum temperatures than Neptune does. Something deeper is happening inside the planet itself. And to understand that, we have to look at what Uranus doesn't have: the internal heat that keeps Neptune warmer. When giant planets form, they don't just accumulate mass, they trap enormous amounts of heat. As gas and material collapse under gravity, compression generates energy, and much of that energy remains stored deep inside the planet. Over billions of years, this internal heat slowly escapes into space, warming the atmosphere from below. Neptune still radiates more than twice the amount of energy it receives from the Sun. That extra internal heat rises through its atmosphere, driving storms, fueling winds, and keeping its upper layers slightly warmer than they would otherwise be. Uranus is different. Measurements show that Uranus emits almost no excess internal heat. It radiates nearly the same amount of energy that it receives from the Sun. Compared to Neptune, Uranus appears almost thermally inactive. That lack of internal heat means there's very little energy rising from the planet's interior to warm its atmosphere. Without that additional heat source, Uranus's upper atmosphere can cool to lower extremes than Neptune's, despite receiving more sunlight. Why Uranus lacks this internal heat remains one of the major mysteries of planetary science. One leading theory suggests that early in its history, Uranus may have experienced a massive collision with a large protoplanet. Such an impact could have disrupted its interior, altering how heat moves through the planet and possibly explaining both its sideways tilt and its unusually weak heat emission. But even today, scientists are still uncertain. With only a single spacecraft flyby from Voyager 2 in 1986, much of Uranus remains poorly understood. And that limited knowledge leaves us with a planet that is not only the coldest, but also one of the most mysterious. The coldest temperature ever measured in Uranus's atmosphere was around -371 degrees Fahrenheit. That makes it the lowest atmospheric temperature recorded on any planet in the solar system. For comparison, the coldest temperature ever recorded on Earth was -128.6 degrees Fahrenheit at Antarctica's Vostok Station. Uranus is more than 240 degrees colder than the most extreme natural conditions on our planet. At those temperatures, gases behave differently, atmospheric chemistry slows dramatically, and energy becomes scarce. The upper layers of Uranus's atmosphere are so cold that even methane, which gives the planet its pale blue color, exists in a delicate balance between gas and condensation. And what makes this even more surprising is that Neptune, despite being farther from the Sun, does not reach temperatures this low. Its internal heat prevents its atmosphere from cooling to the same extremes. Uranus is colder not because it is farther away, but because it lacks the internal energy that keeps other giant planets warmer. And that raises an even bigger question: how much else about Uranus have we misunderstood? Uranus has only been visited once. In 1986, Voyager 2 flew past the planet, giving us our first and only close-up look. The spacecraft revealed a pale blue world with faint rings, a complex magnetic field, and a system of icy moons. But the encounter lasted only a few hours. Since then, no orbiter has returned. Compared to Jupiter and Saturn, which have been studied extensively by multiple missions, Uranus remains largely unexplored. Many of its atmospheric processes, internal structure, and heat dynamics are still poorly understood. We don't fully know why it emits so little internal heat. We don't know exactly how energy moves through its interior. And we don't know whether its extreme tilt is the result of a single catastrophic collision or something more complex. What we do know is that Uranus challenges simple assumptions. The farthest planet is not the coldest. Distance from the Sun does not tell the whole story. Internal physics matters just as much, if not more. And until we send another mission to study it up close, Uranus will remain one of the solar system's most mysterious worlds. It seems obvious that the farthest planet from the Sun would be the coldest, but the solar system rarely follows our first assumptions. Uranus, not Neptune, holds the record for the lowest atmospheric temperatures ever measured on a planet, not because it sits farther away, but because it lacks the internal heat that keeps other giant worlds slightly warmer. It's a reminder that planetary science isn't just about distance and sunlight. It's about internal energy, hidden structures, and processes we're still trying to understand. And in the case of Uranus, we've only just begun. Join us next time as we explore more mysteries of the universe.